Today I would like to share with you about the reciprocating pump. So reciprocating pump is the one of the example of positive displacement pump. However, it's not moved by rotating its parts. So reciprocating means we have a piston, and then piston will move up and down, and that movement reciprocate movement. So that's why we call piston pump as reciprocating pump. Reciprocating pumps can be broadly classified into positive displacement pump and rotodynamic pump. Reciprocating pump is a positive displacement pump which fluid is drawn or forced into a finite space and is then sealed in it by mechanical means. The fluid is then forced out to flow and the cycle is repeated. Reciprocating pump can be single acting or double acting. Among the positive displacement pump, there are pumps in which there is a rotary action instead of reciprocating action, such as gear pump, lobe pumps, and vane pumps. This is the example of single acting reciprocating pump. So the reciprocating means the piston here will move left and right like this. So it is a reciprocate motion. So when a piston moves from left to the right like this, so it will create a vacuum here. So and then it will suck the water from the inlet. So and then when this piston move from right to the left, so it will push all the fluid inside this chamber to the outlet pipe like this one. So single acting mean at one time there is only one motion. So means when the piston is sucked, so only the suction pipe here will fill with water, and then when this piston being pushed to the left side, so only the delivery pipe here will the water will flow in delivery pipe. So and then this is example the mechanism for double acting reciprocating pump. So the double acting here means at one motion of piston here there are two movement. So mean, for example, if this piston move from bottom to the top like this one, so means that liquid will be sucked into this chamber. At the same time, liquid at this chamber will be pushed towards the outlet. So and then this is the mechanism of the piston pump. It will connected by a connecting rod here to the crankshaft. So and then it will connected with a wheel like this. So and then you could imagine when this wheel rotate at certain RPM, so it will move this piston left and right like this one. So and then you could imagine for single cylinder, single acting reciprocating pump, so means that there is only one motion at one time. So you could imagine that the Q here, the flow rate, the behavior of the flow rate is when the flow, when piston suck the water, so means that there are no flow out. So means that the negative flow rate here means fluid only fill the chamber. So and then at the delivery stroke, on this time only the water will flow at the delivery pipe. However, for single cylinder double acting reciprocating pump, we could found that all the time there are water flow in the outlet pipe. However, you need to understand that this motion, okay, when the crankshaft here start to move from this point to this point, actually it will create a sinusoidal motion. So means that it start here, the velocity is quite weak, so and then the velocity will become higher at this point, and then at this velocity, and then at this point the crankshaft is actually near to zero. Before it could move a little bit faster at this point and back to zero. That's why we have the curve for the the curve for the flow rate here, okay, can be shown as this curve. So means that you could see that at a certain angle, so there are no flow rate, because at this point, okay, the piston is actually reached at this end. So mean there are no more flow rate will occur. So and then when it push, so and then the flow rate start to flow. So at the middle of this chamber, so mean when the crankshaft is actually at the top here, so it's on its maximum performance. So means with its maximum velocity. So and then again when the piston stroke at this point, so mean the piston is actually at this location, so means there are no flow rate again. So that's why we could draw the graph here as a sinusoidal graph. So and then I would like to share with you a few important equation that you must remember to solve problem about piston pump. The first one is the flow rate. The theoretical discharge of single-acting reciprocating pumps can be calculated using this equation. So we have Q equal to A ln over 60. So the A here is the cross-sectional area of the cylinder. So means that for this diagram, so the cross-sectional area of cylinder means the cross-sectional here, the cross-sectional for this chamber. You need to calculate using the diameter of the piston or the inner diameter of the cylinder area, as stated here. So and then the L here is the stroke length, as mentioned here. So the stroke length is actually the distance from the beginning here to the end of the chamber of the cylinder area, this one. So this is an L. So and then we multiply with N. So N here is the speed rotation in minutes, RPM. That's why we need to divide with 60 here to get the units of flow rate as meter cube per second. So if the rotation speed here is in second, RPS, please don't divide this value with 60. And then we could calculate the slip of pump. So the slip of pump is actually, the idea is, we know that we have piston here, and this piston need to create a vacuum inside this chamber. So and then to make sure that the vacuum is happen, so we must make sure that the gap between the piston and this wall must be airtight. So if air can be loosened out from this gap, so means the vacuum will not perfectly occur. So the tolerance here means the efficiency of this gap can give us the slip of the pump. So the slip of the pump can be calculated as this equation, which is QT minus QA divided by QT, and we multiply with 100% to get the percentage. So the QT is the theoretical flow rate, and the QA is the actual flow rate. So if we calculate this one, we could get the slip of the pump. Okay, the slip of the pump is usually positive. However, slip can be negative if suction pipe is long, delivery pipe is short, and speed rotation is high. Generally, the higher the speed, the smaller the length. So this is in not a so common situation. Normally, we will get the slip of the pump will be in positive value. Now, I would like to share with you the idea to calculate or to express the displacement of piston. So we could calculate the displacement of piston by using this equation. So how to get this equation? The basic idea is based on this diagram. So for example, we have a piston pump here, and then we have a crankshaft like this. So you could imagine that for this situation, the movement of X here, okay, is actually same distance with the X in this situation. So you could have idea if it start from this point, so the piston is actually start at this point. So and then when it move at certain angle here, so the piston will travel for X distance. So means that the X distance here is actually same with the distance of this one. So and then according to this diagram, we could say that the value of X here is equal to R cos theta, which is the theta actually the angle at this the angle of this one. So and then the R here is the radius of this crank radius. So and then the R here, it is equal to the half of the stroke length. So stroke length actually from here to here. So stroke length means the value of L. So means that if the R here, if the point is at this point, so it's actually stay at this point. So and then if the crankshaft is located at this point, so the piston is actually at this point. So means that the L here is equal to 2R, or the R here, the radius here is equal to half the stroke length. So and then the relation between the rotational speed is shown like this. So omega is equal to 2 pi n over 60. Okay, normally in pump and turbine, we will use equation like this. We have U is equal to R omega. Okay, and then it's equal to pi dn over 60. So we have a pi, we have d, pi dn over 60. Okay, so and then the theta here can be written as theta is equal to omega t. So this is the common equation that I hope you could remember for this topic. So and then after we get the value of displacement, so you must understand that displacement here is distance. So the unit must be in meter in this problems. So and then after we get the distance, the displacement of the piston, so we need to calculate the velocity of the piston. So the velocity of the piston, it can be written as UP, the velocity of piston. P is for piston, and then the simple idea is we do the differential form dx over dt. So this is you could understand the meaning of this one. So dx over dt means the difference of distance in divide by the difference of the time. So length over time is equal to distance. So we differentiate the r cos theta, the value of x here. So we have d dt for r cos theta, and then we could get r omega sine omega t. So we get the sine omega t by replacing the value of theta with the omega t here. So this is the mechanism. So I hope you can understand the idea of displacement of piston like this one, and then the relation between the this is not R, so this is the actually the idea of L. So from here you could get that the L here, the total length of this distance is equal to R. So and then, in this problem, we need to come out with the continuity equation. Okay, so I think this is not something new for you because we already calculate the continuity equation in Fluid Mechanics 1 and Fluid Mechanics 2. So the equation for the continuity equation is the same. It is Q is equal to AV. So we have A cross-sectional area times V. So and then in reciprocating pump situation, we could calculate the flow rate by multiply the A, the cross-sectional area for piston, multiply with the velocity of piston. And it is equal with the cross-sectional area for suction pipe with the velocity of flow inside the suction pipe. And then it can be equalized with the cross-sectional area for delivery pipe multiplied with the velocity of flow inside the delivery pipe. So this is the common idea. I hope you could remember this. So and then previously, I already show you that the flow rate of piston pump is actually not steady. So it can be drawn as sinusoidal graph, something like this. So means that if the velocity is not constant, so the velocity is different time by time. So when velocity is different time by time, so means that there is an acceleration occur on that movement because the velocity is keep changing. So means that we could get value when we have V2 minus V1 over time. So now we need to calculate what is the acceleration for the piston pump. So acceleration head represent the energy required to accelerate the water column in suction or delivery pipe. So the idea of acceleration head here means that the energy that required to push the water to achieve certain value of acceleration. So and then according to the physics calculation, so the A here, the acceleration is actually V2 minus V1 over T, or it can be written as du over dt. So means we differentiate and one more time the value of velocity. So and then we do the d over dt with the velocity that we get from the previous calculation here. So this is the equation for the velocity. So we do the differentiate d over dt r omega sine omega t, and then we could get r omega square cos omega t. So this is the equation for the acceleration head. So and then acceleration head in suction pipe can be calculated by this equation. So I hope students remember this one. I'm not going to show you the derivation of this equation because our aim in this topic is actually to calculate the flow rate later on in a reciprocating pump. So this is the equation. So you need to remember all these two equations. One is for acceleration head in suction pipe, and this one is acceleration head in delivery pipe. So the LS, the LD here, AP, AS, AP, and AD here is, so LS is the length of the suction pipe. So AP is the cross-sectional area for piston. This is the cross-sectional area for suction pipe. So LD here is the length of the delivery pipe. AP means cross-sectional area for the piston, and AD is the cross-sectional area for the delivery pipe. So and then we learn about friction in Fluid Mechanics 1. So means that if fluid moving inside a pipe, they must have major loss and minor loss. And then we learn about pump efficiency in fluid mechanics too. And then in this topic, we also need to calculate the friction loss for reciprocating pump. So because the flow is not steady, means the flow rate is quite fluctuate. Okay, as I show you previously. So the equation of the friction head in suction pipe and delivery pipe can be calculated by using this equation. So the equation is actually not the same with the minor loss and major loss equation. So the idea is F L over D 1 over 2G times the velocity that we have here. Okay. So and then for the delivery pipe, so this is the equation F L D over D 1 over 2G and AP over AD R omega sine omega T square. So and then since friction for suction and friction for delivery vary with the position of piston, or their averages during the suction and delivery stroke can be written as 2 over 3 friction in suction pipe and 2 over 3 friction in delivery pipe, where HFS and HFD are the maximum value of friction head in suction and delivery pipe. Maximum value occur at omega equal pi over 2. So means that we could calculate the maximum losses in suction and delivery pipe by using this equation. So here I hope you could remember this equation. Later on in tutorial, I will show you how to use this equation. So and then work or power done per second. Power of work done per second. We can calculate the power by using this equation. So the power can be calculated using rho GQH, and then we need to substitute the value of H here. So the H here is actually the total head reflect the pump capability. So the HS and HD here is the head of suction and head of delivery. So from this diagram, we could say that head of suction is actually the height from the center line of piston pump here to the level of inlet water. So this is the suction head. And then the suction delivery is the distance from the center line of the piston to the surface of water at the outlet here. So this is the delivery head. So and then to make sure that this pump can be delivered this kind of for this situation, we must include the power calculation with the friction that occur in suction and delivery pipe. That's why in this situation we need to include the value of losses in suction and also the maximum losses in delivery. So the idea is very simple. If we just supply power using the head of suction and delivery head here, means that our total power in our pump here, in our piston pump, cannot deliver water for this condition, because we still have friction here to be overcome. So I hope you could understand why we need to calculate all the situation, include the friction to calculate the minimum power that can be supplied, that must be supplied to the piston pump. So here I would like to share with you another idea in piston pump mechanism. So the idea is the air vessel. Air vessel can be fitted on one or both sides of the pump. on suction and delivery side. They are located close to the cylinder. Volume of air vessel on the delivery side is about 6 to 9 times the volume of cylinder, and then on the suction side 3 to 4 times the cylinder volume. Air vessels serve the following function. 1. Fluctuation in discharge are decreased. Pump can be run at higher speed because there is less danger of separation flow. And the third one is there is less friction loss and hence saving in work done. When air vessels are provided, the flow before air vessel on the delivery side and the flow between air vessel and cylinder on the suction side are varying. Hence, acceleration head are calculated on its length, LSA and LSD. So what is the air vessel? It can be described as this one. So the air vessel means we provide a vessel, airtight compartment like this. We could install it both in suction and also in delivery pipe. However, normally it is enough for us to install the air chamber or the air vessel on the delivery system. Why? Because as mentioned in this slide, so the fluctuation discharge are decreased and also it can create less friction loss. So it means that when we have air vessel here, so flow rate inside the pipe after the air vessel will become steady. Previously, I already showed you that the flow rate, the Q for piston pump will be fluctuated. So it will create a sinusoidal graph. So sinusoidal graph means the flow rate is not steady. So and then in air vessel, the mechanism is simple. When we push water here, so means some of the water will flow inside this air vessel. So and then at the region means when piston is around this area and also this area, the flow rate become weaker and weaker. So at that time, water that store in this air vessel will flow together inside this outlet pipe. So this mechanism will create the flow inside the pipe after the air vessel will flow like a normal flow in pipe. So means that after this in tutorial you will find that the calculation for water inside a pipe after the air vessel will use same equation as we learned in fluid mechanics 1, which is the loss in pipe. So this is shown that the air vessel can make the flow rate become steady instead of sinusoidal curve like this one. So and then in tutorial later on, we will see that the calculation of losses with and without air vessel is totally different. The losses for pipe with air vessel is relatively small compared to the friction for pipe that has not air vessel here. So and then we could calculate the velocity beyond air vessel on delivery side. It could be calculated like this one. So U for delivery is ALN over 60 AD. So this is the speed, the flow rate, and then this is the cross-sectional area. So and then we could calculate like this one. And then the discharge beyond air vessel can be calculated by using the normal continuity equation. So we have AD times UD. And then the discharge in air vessel can be calculated with this equation, which is QA equal QD minus Q equal AP cross-sectional area for pistons R omega sine omega t minus 1 over pi. If QA is positive, water flow into air vessel, and if it is negative, it flows out from air vessel. So the idea of this calculation is to make sure that we have an extra flow rate to be pushed into the air vessel. If our flow rate from the piston pump is not enough, so means that there are no water flow inside the air vessel. So means that our air vessel cannot be function very well. When air vessel is fitted on the suction side, the same expression is valid for QA, but sign get reversed. For air vessel on the suction side, water flow out of air vessel is QA is positive and into it if it is negative. So the idea is normally it can be installed. The air vessel can be installed in delivery and suction pipe. However, the most common practice is we install the air vessel at the outlet because we want to make sure that the flow rate at the outlet is steady and the friction is less compared to the system without any air vessel. So this is just for your notes. If the piston pump is double acting cylinder, so we could calculate the flow rate for air vessel is shown like this one. So and then the power or work done by single acting reciprocating pump with air vessel on both sides is given as this one. So the power can be calculated by rho GQH, and then the value of H need to be calculated as this one. So similar expression can be written for double acting reciprocating pump with air vessel. So later on we will see how to solve problems about piston pump.